Good morning, everyone. Here, I would like to introduce our next keynote speaker, Professor Laurent Bopp. The singer is senior scientist and an adjunct professor at ENS in Paris. He is a prominent modeler with research focus on the links between climate change and marine biogeochemistry. Through more than 200 publications, he has addressed several key research questions, such as how will multiple global stressors affect ocean productivity, fisheries, and the carbon cycle. His modeling results have been included in the IPCC report, and his great contributions make him as the recipient of AGU Ocean Science Voyager Award in 2016. But research is just a part of history. He is also keen on teaching and helping early career researchers. He currently teaches marine biogeochemistry and climate science to graduate students at 3 French universities. In addition, as an IMBeR ICC member, he lectures in the IMBeR Summer School. Today, he will share his latest findings with us on the ocean modeling related to marine biological productivity. Thank you very much.
Good morning, everybody, and thank you very much, Shan, for the nice introduction. Thank you for the organizers to inviting me to give this lecture here today. So I'll be talking about projections using mostly climate models and focusing on biological productivity in the coming decades. I guess what I want to do today is open the house and show you all the uncertainties and what we think we do well and what we think we don't do well, so that everybody knows how well we do in terms of projections of biological productivity. So for those who haven't read the science plan of IMBeR, here I'm tackling the Grand Challenge 2 on improving scenarios, predictions, and projections of future ocean human systems at multiple scale. That's, of course, quite a very large question, so I will restrain myself and only focus on some of these keywords, focusing on projections, mostly ocean systems. I will let the human part aside for this talk, and I will mostly focus on the impact of climate change. Again, leaving the impact of fisheries and other drivers for some other talks, for Lynn's talk, for example, in terms of fisheries. There is another talk, and of course this will be based on works from many different programs, projects, institutions, both at the international level. I mentioned here CEMIP, the Coupled Model Intercomparison Project, FishMIP and MareMIP, which are also projects comparing models and focusing on marine ecosystems. Principally, you see here also some IMBeR regional programs, also looking at this Grand Challenge 2 and some national programs on the right. So there are lots of people working on those topics in different institutions, different programs, both at national and international level. And before I start, let me mention that there is another keynote talk on Grand Challenge 2 given by Eric Galbraith, which I guess will give a coupled ocean-human perspective on these questions, including other drivers like fisheries. Okay, so let's start with maybe the basic in terms of ocean changes, warming and acidification. These two quotes are from the last IPCC report, and you see some of the confidence language that is used here. It's virtually certain that the upper ocean has warmed on the left here, and of course the uptake of anthropogenic CO2 results in the acidification of the ocean, and you see that we have very high confidence that surface seawater has decreased its pH by something like 0.1 since the beginning of the industrial era. So lots of certainty for warming of the ocean and acidification. It's the same for the next decades. Again, quotes from the last IPCC, the global ocean will warm in all RCP scenarios over the 21st century, and you have some projections here, global mean SSTs for the different RCPs that are included in the IPCC report. And it's even more certain for pH with this quote from IPCC, Earth system models project a global increase in ocean acidification for all RCP scenarios. You see that contrary to SST, in which you have some uncertainties depicted by the envelope around the curve here, for the pH, no envelope, almost no uncertainty. All the models, they align on the same line here in terms of decreasing pH. So I guess you would agree with me that we know the ocean has warmed, we know the ocean will warm a bit more depending on the scenario in the coming decades. We know the ocean is acidifying, and we also know that it will continue to acidify in the coming decades, the magnitude depending on the scenario in terms of increasing CO2. That's very clear. We know much more than just these global numbers. We're able to use those climate models to basically project those changes at the regional scale. And here you have, focusing on the Atlantic mostly, the changes in sea surface temperature at the top, and changes in sea surface pH at the bottom for the two very different scenarios, the high emission RCP 8.5 on your left and the high mitigation RCP 2.6 on the right. And you see that the situation diverges in the middle of the century, depending on the two scenarios, and we end up at the end of the century with two different worlds, the RCP 8.5 on the left and the RCP 2.6 on the right. So I would say that in terms of warming and acidification, of course, we have progresses to make at the regional scale maybe, and in some specific cases, seasonal cycle, extreme events, etc. But we have quite a clear understanding on the mechanisms and on the projections. But what about marine productivity? I guess if I ask you the question, is marine productivity decreasing today or increasing today, you would be a bit annoyed. Depending where you come from, what's your background, you may have different answers. And it's the same for the projection. As I will show in a moment, we are still navigating in an ocean of uncertainties in terms of changing NPP as a response to climate change. So the progresses that have been made over the past 10 years, maybe, has been mostly due to the fact that we've integrated biogeochemical models in the climate models. They stay very simple, I would even say simplistic in some ways. So those biogeochemical models that we have now in climate models are NPZD type models, you know, only one generic phytoplankton, one generic zooplankton, and some of them have evolved into dynamical green ocean models with a few phytoplankton, a few zooplankton. In most of these models, the representation of biology is still very, very simple. There is no representation of upper trophic levels. The biogeochemistry and the biological processes also very, very simple. But still, we are using those models to tackle the question of the impact of climate change on marine productivity. So this is what is said in the last IPCC report, based on this first set of climate models that have embedded biogeochemical modules. So at the global scale, open ocean NPP is projected to decrease globally, and this will depend on the RCP scenario. And you see medium confidence. And the estimated decrease in terms of quantity will occur by up to 9% by 2100 under the high emission scenario RCP 8.5, and for that we have low confidence. And the figure that you have at the bottom of the slide here depicts this very large uncertainty. And you see that the envelope around the line, so the curve are the model mean for the projection, and the envelope is based on the differences between the different models. If we focus on the red scenario, which is the red curve here, RCP 8.5, the model mean tells you that NPP might decrease by 10% at the end of the 21st century, average over the entire ocean. But you see that the red bar here depicts the uncertainty. So some models project no change in global mean NPP, and some models do project a very large decrease of global mean NPP. Lots of uncertainties, very different from the situation I was depicting for warming and acidification. And if we go at the regional scale, maybe the situation is even worse. We have very large regional contrasts between latitudes and between ocean basins. Again, this is a model mean for the end of the 21st century in response to the RCP 8.5. You see that productivity may decrease by up to minus 50% in the North Atlantic, by up to minus 20% in the tropics. It might increase in the Southern Ocean, it might increase in the Arctic Ocean. So large contrast between latitudes. But again, when you look at the regional scale, we lack robustness here. So very low confidence and lack of robustness when zooming in at the regional scale. And even when the models agree on the sign of change, which may be the case in the North Atlantic or in the tropics, they may not always be a consensus on the mechanisms that is responsible for the change the models do project. So it's a complicated story, and of course we need to do better in the coming years. Just one point on the main mechanisms. Why do these models project a global mean decrease of NPP in the coming decades? It's mostly linked to ocean physics and to the fact that we expect a more stratified ocean with global warming, more stratified ocean, meaning less nutrient supply from below, meaning more nutrient limitation and less NPP. So it's a bottom-up control on NPP. So we still have uncertainties, but of course we still have to use those projections to get some answers on the potential impact of climate change on marine ecosystems, upper trophic levels, diversity in the ocean, etc., etc. And that's the case at the global scale. It's also the case at the regional scale. So I show you two examples in which those projections have been used, responding to some of these questions. So the first example is the one that Alistair already mentioned yesterday. It's this very recent paper published by the FishMIP team, Lotze et al. In PNAS, just last week, I think, in which they've used the projections from the climate models, temperature, NPP, oxygen, currents, temperature, etc., and they forced 6 different ecosystem models, which are very different by nature, some species-based models, some size spectrum-based models, and it's the first model intercomparison of that type, using different ecosystem models at the global scale, with different scenarios, the 4 RCP scenarios, but also different Earth system models, trying to bracket the response of these different models in terms of NPP. And what you see here is that the NPP changes I was presenting before are fundamental for the projections of these marine ecosystems. So you see again the 4 scenarios, RCP 8.5 in red, and you see the uncertainties, which this time is taking into account both the climate models uncertainty and the ecosystem model uncertainty. The overall response here is a decrease of total marine animal biomass at the end of the 21st century between -5% for the RCP 2.6 scenario to -17%. So a higher decrease than the one we are simulating for NPP. And another interesting result from this model intercomparison study is this consistent trophic amplification of that response. That's what you see here. It's again a figure from the Lotze et al. Paper. You see the change of NPP for the different RCPs in light green, and you see in blue the change in the biomass of the high trophic level. And you see that there is an amplification of the response across the different trophic levels, from NPP to phytoplankton biomass, zooplankton biomass, and large animal biomass. So despite the fact that we have uncertainties on the NPP, we are still using these projections to have an idea of the potential effect on marine animals in the ocean. Another example is biodiversity. And I give you an example of a paper that is just in revision in Cell now by IMBeR et al., in which they've used the Tara ocean data to create statistical model to relate diversity, here alpha diversity, to the environmental conditions, temperature, chlorophyll, mixed layer depths, and some other nutrients and some other variables. And before they did that, they split the different functional or taxonomic groups, and they derived one statistical model, or lots of different statistical models per each of these different taxonomic groups. And what we did in that paper was to use those projections, NPP, temperature, and some other factors, nutrients, and ocean physics, to try to project the potential impact of climate change on diversity for the different taxonomic groups. I give you just one example here on copepod diversity, you see some places like in the Arctic or North Atlantic where alpha diversity is increasing in response to mostly increasing temperature, but also to change in NPP, and the same in the Southern Ocean. So it's another way to use those projections, combining this with lots of data, the Tara data here, and some statistical model to work on diversity. So I guess we progress. We have uncertainties, but we progress, and we've derived lots of quantities, variables that are responsive to future climate change, as I explained in the past minutes. Of course, we need to do better. That's what I was somehow repeating the past minutes. And I guess we have two main steps for the coming years that I will try to illustrate. So we have to better understand the differences between the models and maybe to constrain the uncertainties, to constrain the projections. That's the first objective, I guess, that we have remaining. Why do we have such a difference between the models? How can we explain the differences? And can we constrain the projections, reducing the uncertainties? And the second point, the second objective is about adding new processes, because as I said before, we still use very simplistic model, not taking into account the complexity of the system we represent. So we need to complexify, to be sure that we haven't let on the side some of the uncertainties maybe that we should take into account. Again, we need to go maybe at finer space scale if we want to be more useful in terms of management of these complex systems. And we also need to focus on shorter timescales. Most of what I've shown is at the end of the 21st century. So we need to do better. So my two sentences here that I repeat to my son once a week at least: clean up your room. That's what we need to do when we do the projections. And of course, once the room is cleaned, we need to open the window for fresh air. That's adding the new processes and complexifying the system from the outside. So I will try to illustrate those 2 points with examples from recent literature. So clean up your room. How can we explain the differences between the models we're using? So I have 3 examples. The first one is the Arctic Ocean. In fact, when you look at the different models in the Arctic Ocean, they diverge in terms of the response of NPP to future climate change. So here on the top graph, you have the extension of the permanent ice zone as simulated by those coupled models over the historical period and the future in response to RCP 8.5. Of course, they differ in terms of the timing of the disappearance of the permanent ice zone here, but they all show the same trend. That's not a surprise. When you look at NPP, that's the bottom graph, so it's the integrated NPP over the Arctic Ocean. You see that the models, they start from very different initial conditions. Some have much higher NPP than what's observed, and some others are much lower NPP than what's observed. But they also diverge in terms of the response to climate change, with some models here increasing NPP in the coming decades, and some other models here stabilizing or even decreasing NPP. So even on the sign of change, NPP to climate change in the Arctic Ocean, we have some differences. And so the paper by Van Koppenel here, published some years ago, looked at those differences, which are here illustrated by 3 of these models. The GFDL model here, increasing NPP over the 21st century, and this other model here, the IPSL model, peaking in the mid-21st century and then decreasing NPP in the second part of the 21st century. The climate signal is quite similar. The NPP signal is completely different. And what Martin van Koppenel showed here is that we can explain those differences. We understand those differences. They are explained by the timing of the oligotrophy onset in the Arctic Ocean. So you have those 2 compensating effects: less sea ice, less light limitation for Arctic phytoplankton, but at the same time, a more stratified Arctic Ocean, meaning less nutrient supply from below, and maybe leading to oligotrophy and more nutrient limitation. So those 2 mechanisms, they exist in all models, but it's the compensation between those mechanisms that does not happen at the same time. And in the IPSL model, we start with a lower stock of nutrients, and so we reach oligotrophy much earlier in the 21st century. In the GFDL, still lots of nutrient before the end of the year. So we have a way to constrain the projections by looking at the nutrient cycles as simulated by those models, and then we would be able to constrain the NPP projections. That's one example. I have another example in the upwelling areas. There's this big question about the Bakun's hypothesis, a larger temperature gradient across ocean and land, intensifying winds, and then higher upwelling, as Lynn was was discussing. But when you look at climate models, the systems are not so simple. And depending where you are in the upwelling regions, you may find increasing upwelling intensity or decreasing upwelling intensity. There's this very nice paper by Rikaszewski in 2015, in which he analyzed the couple model in quite a precise way. And what he showed is a consistent response of wind intensity in the eastern upwelling systems associated with a poleward migration of the atmospheric high pressure cells. And in fact, if you see the maps here with the robust change, so we are looking here at the change in upwelling favorable winds at the end of the 21st century in the RCP 8.5 scenario. And what Rikaszewski showed is that in all of the systems, we find the same signature of climate change with intensifying winds in the poleward part of the upwelling regions, maybe like in the Benguela upwelling system that Lynn was talking about, but decreasing or weakening winds in the equatorward part of the upwelling systems. So it's not the Bakunin's hypothesis here, it's a bit more complex. It's linked to this migration of atmospheric cells, but at least the different models, they seem to converge on that major trends. My last example is here. Another example of constraining projections. So here I'm focusing on the NPP projections for the tropical oceans, in which the models diverge, some projecting no change in NPP for the entire tropical ocean, and some projecting a large decline of NPP for the tropical ocean. And that's what you have on this graph here on the y-axis. That's the sensitivity of tropical NPP to warming. So we are looking at NPP change per degree of warming, and each of the dots here is representative of one of the CEMIP model. So you would have the model projecting a large decrease here on the bottom left, and you would have the other models projecting no change, no decrease in the tropical ocean at the top of the graph. So what's been done here is the identification of an emergent relationship across models. That's been published in 2017 by Kwiatkowski et al. We found that the models that do project a large decrease of NPP in response to climate change, they also simulate a large response of NPP to ENSO, to El Niño. And that's what you see here. Reversely, the models that project only very little change in response to future climate change, they also project a very weak signal in response to El Niño or to ENSO variability. And this relationship seems to hold for the 10, 12 models that we've looked at. And so we can derive this emergent relationship across the different models. And the nice technique here that we apply, it's called emergent constraint, is the fact that we can constrain the projection here based on some observations that we have on the x-axis. So again, the x-axis is the response to ENSO, to El Niño, and the y-axis is the response to future climate change. And so that's what's done in the 2017 paper. We have indications from remote sensing of the response of NPP to ENSO variability. Here, those are the dotted and vertical lines on that axis. So you can use what we observe here on the bottom right, the emergent relationship to project the observed constraint on the projected axis. So that's a way to reduce the uncertainties using observations, selecting, if you want, the models that do represent what we observe in a proper way. And if you do that, that's the probability density function of the response of NPP per degree of warming. The black one is the unconstrained PDF, taking into account all the CEMIP models, all the couple models. And if you use the observations and this emergent constraint technique, you reduce the uncertainty, and you have here a peak that tells you that tropical NPP would decline by 3% per degree of warming in the coming century. So again, that's another way, maybe a novel way of reducing the uncertainties across the different models. Second point, adding new processes. In the past examples, I've been still using these very simple models, limited representation of biology in those models. So I will try to give you here some examples of new things not taken into account in the models that we are using now. First example, physics. Maybe we need to account for surprises in the response of ocean physics to climate change. And here I give you one example which is linked to Greenland melting. You know, there's lots of debate in the climate community about the rate of Greenland melting in the coming decades. It's very complicated to predict. You may know also that the climate models, they don't include an explicit representation of continental ice sheets. So we have somehow to mimic Greenland melting in those models. And we do that in a very, very conservative way, if you want, adding fresh water in the North Atlantic, mimicking a slight melting of Greenland. So what we've done in that paper is to explore the sensitivity of the ocean NPP to scenarios of Greenland melting, of extreme Greenland melting here, so idealized scenarios in which Greenland melting may account for an additional 40 centimeter in 2100 or even up to 1 meter, 0.7 in 2100. And what you see here is that the North Atlantic is responding very significantly to this addition of fresh water in the North Atlantic. So the large impact in the North Atlantic may range up to 2 times the reduction that is simulated just from the RCP 8.5. And the mechanism is quite simple. You add all this additional fresh water in the North Atlantic. The stratification induced by this addition of fresh water would be very severe, inducing a reduction in the nutrient supply from below and a larger reduction of NPP. So that's a way to explore those surprises in the climate system. And that's what you see on the graph here, a large melting of Greenland and a drop of the North Atlantic NPP here from 4 petagram to almost 2 petagrams, so a very rapid drop of the North Atlantic NPP. That's for the ocean physics. Another example for more complex biology or biogeochemical property. The models we use are simple. I said that a few times. One of the simplification or major simplification that every group is using at the moment is the fact that we based organic matter production on Redfield ratio. So we assume that there is no variability in the carbon to nitrogen and carbon to phosphorus ratio in the organic matter, for sake of simplicity. Because it would cost, in terms of computing power, much more to represent all this biological complexity. And of course, if you do that, you simplify the system. You can't account for adaptation, maybe, of the phytoplankton cells to change in the environmental conditions, and you may miss some of the important response of your phytoplankton to future climate change. So here, I just mentioned that we, in a paper published last year, used a more advanced version of the biogeochemical model PISCES here, in which we integrated an explicit representation of this variable stoichiometry in the organic matter. So you have to follow phosphorus, nitrogen, carbon in every organic matter pool of your model. And we've run climate change scenarios with this advanced version of the biogeochemical model. What we seem to get is not a large impact on NPP, at least on that time scale, 21st century, but we have a significant effect on food quality because the C2N and C2P ratios are changing quite a lot. And in fact, the nitrogen to carbon and phosphorus to carbon ratios are decreasing, maybe reducing the quality of food for the upper trophic levels from phytoplankton. So again, that's an effect that is not taken into account in most of the models, ecosystem models that I showed before. The impact of decreasing food quality on upper trophic levels, again, not taken into effect in the fish MIP projections that I was describing. So we may have a few more processes like this to explore in the coming years. Last point here, in terms of complexifying and time and spatial scale issue, projections to predictions. So I've been focusing at the end of the 21st century, where the signal in response to climate change is quite clear. But of course, for many of the questions we have, especially at the regional scale, this time scale, the end of the 21st century, that's not enough. And I'm sure you would love to have more information over the next decade or maybe 20 years. You know, the managers, the question is, yes, but 2020 or 2030, what's the response I could expect from climate change? It's very difficult because the climate models I'm basing my work on, they generate their own climate variability. And that's an example here, RCP 8.5, NPP. And you see that the variability of the different models, so that's internal variability, mimicking natural variability, is very large, and somehow is hiding the climate change signal. So those models, they are of no use if you want to focus over the next decades, 2010 to 2030 here. The internal variability, again, tends to dominate on these timescales. So what can we do? So there's this new emerging field in the climate community in which climate modelers use the same climate models, but they try to use methods from the weather forecast fields, like assimilation in the climate models. So you would assimilate temperature, maybe winds, maybe salinity in the ocean, so that you would run your model in an assimilated mode for a few years, and then maybe we have some predictability over a few years, maybe a decade in some regions of the ocean. So here we are really in between climate and weather forecast, but we are focusing on a few years. So there haven't been much publications on those techniques applied to marine biology or marine biogeochemistry. Many papers over the last years on the North Atlantic circulation, on the Southern Ocean, etc., using those kind of techniques. I'm just showing you this paper that was published a few years ago by Seferian et al., 2014, here, looking at the potential predictability of marine productivity. So again, you assimilate in your models physical variables, temperature, winds over the last decades, and then you run your model for a few years to look at a forecast. And then you could do that in the past, and you could check if you have some prediction or some predictability. So that's been done by Roland Seferian here, and what he shows in red on that map is that in the tropical Pacific, it seems that we have some predictability on a time horizon of 3 to 5 years. So maybe we would be able to predict the potential evolution of NPP in some regions over a few years, taking into account internal variability here. So I'm not talking about climate change signal here, it's really proper internal variability. Okay, so maybe I will conclude here. So in terms of projections, I guess, as you've seen, we have a lot more to do. I haven't touched the regional scale very much. We have lots of downscaling methods that are in use in the community, using statistical models, using dynamical models to downscale what those global models are telling us. I can say also that the next generation of coupled climate models will have increased resolution in the ocean from 1 to 2 degrees as of today, maybe to half of a degree, and some models even to a quarter of a degree. So even the global models will help us to look at the regional scale in the coming years. We need to better combine different types of modeling approaches. I guess the example of FishMIP is quite good in that regard, looking at species-based model, size spectrum-based model, and confronting those different models. We learn a lot by doing that. We need to do the same maybe in biogeochemistry, combining different approaches here. I think the predictability theme, it's like a new frontier for us. We've been studying the impact of decadal variability or short-term variability on marine ecosystems, but we haven't worked so much in predicting this variability in the coming years. Here we can learn a lot from the physical realm and all the studies that have been published in the past years. And then here I haven't tackled down the question of scenarios. I've just used the RCP scenarios from the climate community, if you want, as they are. But of course, many other things are changing in the ocean and may affect all of the responses I've showed you. Fisheries, of course, maybe pollution, geoengineering options that Alistair mentioned the other day. We may need also to explore those different scenarios, combining the RCPs with those new scenarios in terms of fisheries, pollution, or some other stuff. I thank you.
Thank you very much. I think we have a couple of minutes. Any questions? Oh, hello. Please pass the mic to that gentleman.
Thank you for a most interesting talk. And I was particularly delighted to hear you emphasize the importance of short-term variability and how to predict it. I sit on the SSC of a Fisheries Management Council that's responsible for the fisheries in the federal waters off Alaska. We try to get our estimates of fish every year from trawl surveys, and we project out 1 to 2 years as to what the fishing will be, and we set the amount of fish that can be taken 1 year in advance. Anything beyond that is academic. It's very important for our understanding of climate change, but it's irrelevant to the fisheries management scheme. You talk to the fishing industry people, because they're all there lobbying, and they'd like to know maybe 10 to 15 years out. That's the horizon they have for investing in a new ship. $100 million to go chase a few pollock. So we have to be thinking, if we're talking about bringing the human interactions to the climate change issues and all of those things to the ocean, we have to be really cognizant of the economics and political reality that the horizon that people are working with is in that short period you're mentioning. So I just wanted to make that comment because it's relevant to the first speaker as well, that the modeling really needs to focus on the short term. And we get surprises. 2 years ago, we lost 70% of the Pacific cod population in the Gulf of Alaska in 1 year. It was not fishing. It was a warm event, and the physiology meant that they starved to death. So how do we get to that level? Thank you.
Yes, maybe just in response to that comment, in the weather climate community, this time window, if you want, from the season to a few years, maybe from 10 years, which is the one we'd like to focus on. It's been termed the gray zone. We have skills in terms of projecting long-term climate change. We have skills maybe to project weather, of course, maybe some skill in seasonal predictions, but in between, 1 year to 10 years, it's very difficult. So I guess we have to do more. I'm presenting, or at least I presented a few ideas in that direction, but I completely agree with your comment, yes.
Thank you. Anand? Oh, yeah. Could you pass the mic?
Hello? Yes. Well, I'm on your left away, okay?
Okay.
A very nice presentation, Laurent, and so thanks a lot, okay? And very honest, actually, showing that we have a lot of uncertainties. And the unknown is very large. Okay? Would like to refer to the magic triangle that Alistair Hobday shown yesterday, you know. He told us that how to learn faster is to take into account of the models, the observation, and the experiment. Okay, so I do believe in that, actually. And regarding your presentation, you have shown evidences that you will try to stick to observation or to introduce the result of observation. You are able to improve your models. First point, I believe in that. Second point, you need to introduce more complexity in your model. Especially you have to reproduce or to simulate the primary production and to take into account those different species of phytoplankton. Okay? So I also believe in that. What would be your expectation as regards the export production? Okay? There, how are you really able to produce a realistic simulation of the carbon export production to ocean interior?
Yes. In fact, when you compare the different models in terms of export, which I haven't shown here, it's quite interesting, and maybe it's quite counterintuitive, but you have much less differences between models in terms of the response of carbon export to climate change than in terms of NPP. And this seems counterintuitive because we think nutrient, then NPP, and then export of carbon, which may be even more complicated because of the different processes that control exports. So we think if we have lots of uncertainties on NPP, these uncertainties should propagate to the exports. But if you compare the models, we have much less differences or much less uncertainty in terms of export. That's because somehow the exports, as simulated by the models, is almost compensating the nutrient input. So it's more linked to the physics and maybe much less to the nitty-gritty of the representation of the phytoplankton types and heterotrophy, etc., in the upper layer. So I guess that's an interesting point. The other interesting point that I like to make is that I've started to look at how export processes are represented in those models. It's very diverse. Some are based entirely on the ballast hypothesis. Some others only base their export functions on the size of the particles. And some others, they just use Martin curves. But somehow, when you look at the export ratio, they kind of agree on the variability of these export ratios at least across latitudes. So I guess not as much has been done on exports than on NPP, and we may want to look a little bit more on those processes and the controls on export in the different models, but I think I'd like to mention again that counterintuitive response, less differences between models in terms of carbon export than in terms of NPP.
Okay, one more question.
Okay, Laurent, I'd like to know how the coastal ocean is taken into account in these global models, and if you have the information, how the change in the coastal ocean has an impact on the change in the global ocean in terms of net primary production, for instance.
Yes, so the first honest response is that in those models, the coastal ocean is very badly represented. Just imagine that the mean resolution is maybe 1 to 2 degrees. So you have like 200 kilometers, one cell, everything is homogeneous in that cell. How would you represent the continental shelf and all the processes that are important for the coastal ocean? So in those very coarse resolution model, looking at the coastal ocean is, I guess, not a good thing to do. With the increasing resolution of the global models or with the use of downscale regional model, of course, that's a possibility. We've started to look at the impact of changing riverine nutrient inputs on global NPP, on ocean carbon uptake in one of these global models at higher resolution. It has an effect, of course, very strong locally, a bit less when you integrate globally, even in terms of NPP, but of course it's also a direction we need to take to develop the processes included in these models for the coastal ocean, which is mostly not the case today.
Thank you very much. Due to the limitation of time, we have to stop now. If you have more questions, you can contact Professor Laurent Bopp afterwards. Okay, thank you very much.
Merci
Thank you
beaucoup.
again.